Let's get started on your day 4 notes over inverse functions. And today we're going to be using composition of functions to verify inverse functions. So questions for today will look like, are these two functions inverses? We're going to be using composition to verify that. How does this work? Because inverse functions undo each other, when we compose them, we put one entire function inside the other function. They should undo each other, and if you get the input value of x as a result of that, then they are inverse functions. So here's what the rule looks like. If f of g of x equals g of f of x, which equals x, then that means f of x and g of x are inverse functions. Now, if you get something that does not equal x when you compose them, they're not inverse functions. So let's write that down. They are not inverse functions. Inverse functions if the output does not equal x. And another thing that we're going to be doing today is we will be composing both ways. Okay? So we're going to be composing f of g of x and g of f of x. So let's look at our first example right here. It says determine by composition of functions if each set of functions are inverses. I'm given this first function, f of x equals 3x plus 2, and the second function, g of x equals 1/3 x minus 2. Let's look at f of g of x. What I'm going to do is I'm going to write f of x, which is 3x plus 2, and instead of putting an x, I'm going to put parentheses there. Inside of those parentheses, I'm going to put g of x. So I'm going to put this entire function in for x right there. So 1/3 x minus 2. And now let's simplify this. I'm going to distribute the 3, and I get x minus 6. 3 times negative 2 is negative 6. Then plus 2. And when I combine like terms, I get x minus 4. Do I get x as the output when I compose f of g of x? No, I get x minus 4. When this happens, that means that g of x does not equal f inverse of x. Okay, they are not inverse functions. Now, notice up here, I put a little asterisk with asterisk. Did I say that right? Asterisk with, and it says compose both ways. But when we already compose it one way and we get x minus 4, we don't get x. You don't need to compose it both ways if the output is not x on the first try. So let's write that down. Do not need to compose both ways if the output does not equal, right? That's the equal sign with a line through it, does not equal x on the first try. Okay, so that means we composed f of g of x. We did not get x. Therefore, g of x does not equal the inverse of f inverse of x. Sorry. Let's look at number 2. This says for x is greater than or equal to 0, f of x equals 2x squared minus 4, and g of x equals the square root of 1/2 x plus 2. So we're going to compose these two functions to determine if they are inverses. Let's compose f of g of x. And notice that we have a domain restriction here for x is greater than or equal to 0, because this is a quadratic function, and if you recall, a quadratic function takes a shape like this. That's what that would look like. And it's not a one-to-one function. It doesn't pass the horizontal line test, which means its inverse would not be a function. So we have a domain restriction so that this function would actually look like this. It would be half of the parabola. So we've got that domain restriction there. So let's compose f of g of x. And the first thing I'm going to do is write the outside function. So 2, and then I'm going to put parentheses where x is, and I'm going to write everything else down. And inside those parentheses, I'm going to put g of x. So if you need help composing functions, I do have a video of composition of functions, actually several videos, and I'll put a link to those videos in the upper right corner if you need some help composing functions. So now let's simplify this. Well, the first thing I need to do if I'm simplifying using the order of operations, I know that I need to apply this exponent first, right? Before I do any kind of multiplying, I need to simplify the exponents. Notice I have a square root symbol under or inside the parentheses and a square outside the parentheses. Those undo each other, and I'm now left with 2 times 1/2 x plus 2 minus 4. Now I can distribute that 2 into every term inside the parentheses. 2 times 1/2 x is just x. 2 times 2 is positive 4 minus 4. Those cancel, and I'm left with x. So that worked. When you do get x as your output, you need to compose it the other way. I'm sorry, I didn't write that right. G of f of x. So we composed f of g of x. Now let's compose it the other way. G of f of x. So in this case, I'm going to put f of x inside of g of x right there. So I'm going to write the outer function first, which is g of x. There's my radical. 1/2 times, I'm going to replace x with a big set of parentheses, then plus 2. Inside those parentheses, I'm going to put what f of x equals, which is 2x squared minus 4. Now let's simplify what's underneath the radical. The first thing I'm going to do is distribute that 1/2 into every term inside the parentheses. So I'm going to rewrite this radical. When I do that, I get x squared minus 2 plus 2. I can simplify that. I get the square root of x squared, which equals x. And so again, I get an output of x. Now I have f of g of x equals x, g of f of x equals x. So let's write that down. F of g of x equals g of f of x, which equals x. Therefore, yes, these are inverse functions. I probably should have written no at the top of the other one, but there we proved this is all the work that we use to prove that these two functions are inverse functions. Remember, you need to compose both ways to verify. Okay, let's move on to example number 3. Here's another quadratic. So we're given a domain restriction, and it says for x is greater than or equal to 1, f of x equals x minus 1 squared plus 2, g of x equals x plus 3. We need to determine if they're inverse functions. So let's first compose f of g of x. So I'm going to write f of x. And this is really interesting because I have, inside my parentheses, I have x right here. And right here, I just have a linear function. So what I'm going to do is I'm going to write those parentheses and then minus 1 squared plus 2. And in place of x, which I just put an arrow to right here, I'm going to put x plus 3. Okay, do you see what I did there? I replaced, this concept of substitution is really hard for some students, and that's okay, you're not alone. Right there, I replaced it with x plus 1. Everything else, the minus 1 squared plus 2, I wrote there. I kept it where it is. I just, instead of writing x, I wrote x plus 3. So now let's simplify what's inside those parentheses. Positive 3 and negative 1 is positive 2, so I get x plus 2 squared plus 2. And off to the side, you could do x plus 2 times x plus 2, that's x plus 2 squared, and you would get x squared. And then if I FOIL this, right, x times 2 is 2x. Inside 2 times x is 2x, 2x plus 2x is 4x, and then the last terms are 2 times 2, which is positive 4. So I get x squared plus 4x plus 4, and then I can bring down this plus 6, which I can already tell that I don't get an output value of x. Okay? Therefore, f of x does not equal g inverse of x, and g of x doesn't equal f inverse of x. No, these are not inverse functions. You could also write it like this: f of g of x does not equal x. Any of those things that I wrote, I would take as a teacher. You would probably, if you're watching this and I'm not your teacher, you need to ask what your teacher prefers. Like, do you want to write this when I'm saying it's a function or not? I mean, if they're inverse functions or not, or can I just write this? You know, what do you prefer? I always say it's better to write too much than too little. And that's really a good strategy if you're wanting to maybe eventually go to calculus, because you don't get points taken off for getting things wrong. You get points added for getting things right. So let's move on to maybe some more difficult functions. So we're now proving if two functions are inverses. Oh, you know what? I do want to point out the previous example. One was a quadratic and one was linear. We already know the inverse of a quadratic is going to be a square root, but you still need to show your work in that kind of example. So, looking at number 4, f of x equals x cubed plus 2, g of x equals the cube root of x minus 2. So let's first compose f of g of x. And I'm going to write the outside function first, which is f of x. So I'm going to replace x with parentheses. Everything else is going to stay there. Inside those parentheses, I'm going to put g of x, which is the cube root of x minus 2. So now let's simplify. The cube root and a cube undo each other, and I'm left with x minus 2 plus 2. Those cancel, and I'm left with x. Yep, that works. So it worked that way, and because it worked that way, now we need to compose it the other way. G of f of x. In this case, the outer function is g of x. So I'm going to write the cube root of x minus 2, and instead of writing x, I'm going to write x cubed plus 2. Now let's simplify this. First, I'm going to simplify what's underneath the radical. So those two are going to cancel, and I'm left with the cube root of x cubed. The cube root and the x cubed, they cancel. I'm left with x. Bada bing, bada boom. That means, yes, these two functions are inverse functions. I could say that f of g of x equals g of f of x, which equals x. I could write f of x equals g inverse of x, and g of x equals f inverse of x. Let's move on to example number 5. F of x equals e to the power of x minus 5, and g of x equals the natural log of x minus 5. When I first look at this, I'm like, oh, exponential function, I have a logarithmic function, I have a 5 in there. Sure, they're inverses. Let's compose them. First, let's compose f of g of x. And when I do that, I'm going to write the outer function, which is e to the power of x, which is, I'm going to replace with the natural log of x minus 5, and then minus 5. When I look at this, I can actually not simplify this any further than this right here. I don't need to go on. This is the output. Is that x? It is not, which means no, these two functions are not inverse functions. F of x does not equal g inverse of x, and g of x does not equal f inverse of x. You could also write f of g of x does not equal x. I do not get an output of x when I compose them. Let's move on to example number 6. Number 6, I've got two rational functions. F of x equals 5x plus 6 over x. G of x equals 6 over x minus 5. So I am going to compose f of g of x first. So f, and I'm actually going to write this like this first. 5 times x plus 6 is in the numerator. 5 times x plus 6 over x. And inside those parentheses that I wrote, I'm going to put g of x, which is 6 over x minus 5. 6 over x minus 5. Okay, so now let's look at our numerator first. Let's simplify what's in our numerator. I'm going to focus on that. When I need to distribute this 5, and when I do, I'm going to multiply it times the 6, right? So if you want, some students really need to write, okay, 5 over 1 times 6 over x minus 5. That's how that works. So I'm left with 30 over x minus 5, then plus 6. I'm going to write that over 1. I know when I'm adding or subtracting rational expressions, I need to get a common denominator. My common denominator is x minus 5. Everything over here needs to be multiplied by x minus 5. When I do that, I get 30 over x minus 5 plus, I'm going to go ahead and distribute the 6. 6x minus 30 over x minus 5. And now I can cross out, okay, so I'm just probably going a little fast here. Now I have a common denominator. I can combine like terms in my numerator. I can eliminate the 30 and the negative 30, and I'm left with 6x over x minus 5. Okay, that's just the numerator. Now we've got 6x over x minus 5 divided by what's in our denominator, which is 6 over x minus 5. When I'm dividing fractions, what do? Keep, change, flip. So 6x over x minus 5. Change division to multiplication. I flip the second fraction, which is x minus 5 over 6. And now I can pre-simplify, right? So x minus 5, I can cancel those out. And I'm left with, the 6 here and the 6 down here cancel each other out. And I'm left with x over 1, which is just x. So I've now shown that those are, yes, inverse functions when composed that way. We're not done. Now we need to compose g of f. Oh, it's not writing. Now we need to compose g of f of x. Okay, so function g is 6 over x minus 5. So whatever x is, then minus 5. X in this case is, I'm going to zoom out for just a second, 5x plus 6 over x. 5x plus 6 over x. So now I need to simplify what's in the denominator, right? Which is 5x plus 6 over x minus 5. What I'm going to do is get a common denominator. That should be minus 5 over 1. My common denominator is x, which means I need to multiply the denominator and the numerator by x to get that common denominator. So now I've got 5x plus 6 over x minus 5x over x. And now I can combine like terms in my numerator because I have a common denominator. So positive 5x and 5x cancel, and negative 5x, sorry, because that's a minus, right? Positive 5x and negative 5x cancel, and I'm left with 6 over x. So what we actually have, that 6 over x is in our denominator. We have 6 over 1 divided by 6 over x. Remember, dividing fractions, keep, change, flip. So 6 over 1 times x over 6. I can simplify. The 6 and 6 cancel. And I'm left with x over 1, which is just x, right? So, yes, these two functions are inverse functions. I can say, f of g of x. Let me change colors here. Let's write, f of g of x equals g of f of x, which equals x. Therefore, they're inverse functions. F of x equals g inverse of x, and g of x equals f inverse of x. So yes, we have proven that these two functions are inverse functions, and all of this work that we just did proves that. So good job on today's notes, and that concludes today's notes over proving two functions are inverses using composition of functions. I hope it was helpful.